Hey folks, my name is Nathan Johnston. Welcome to lecture 15 of vector calculus, which is again all about vector line integrals. Okay, so in our previous lecture, we introduced vector line integrals and talked about how to think about them and came up with a formula for computing them. Today's all about examples. We're going to do a bunch of examples of computing these and talk about how to think about them physically. Okay, so the most common physical setup for a vector line integral is it represents the amount of work done by a force on an object. Okay, so sort of the setup is if you've got a vector field that represents a force being done on an object, so like gravity pulling an object down or wind trying to push an object around space, something like that. The vector field is representing the force, and then you've got an object following some path. Then the vector line integral, it represents the amount of work done by the force on the object. In other words, the amount of energy that's put into that object by the force. Okay, so let's do a couple examples sort of along these lines. And let's start off with this one where the force, the vector field, is just gravity. Okay, so suppose they've got a ball rolling down a curvy hill along this path in R3, okay, where t is going from 0 to pi. Okay, and let's say that it's rolling down the hill because gravity is acting on it. Okay, it's just acting on it according to this force field here. Okay, no x component, no y component, and it's just pulling it straight down with a force of, negative 9.8 newtons. Okay, find the work done by gravity on the ball. In other words, find the amount of kinetic energy that this gravity force is putting into the ball as the ball rolls along that path. Okay, so we're just going to do the vector line integral. Okay, so work is the vector line integral. Remember, this is just our notation for the vector line integral of this vector field along this curve C. Okay, and the way that you compute it is you take your vector field, which is this right here, and you plug your path into it. Okay, and we just get 0, 0, negative 9.8, right? There's nothing to plug in here because there are no x's and y's and z's in the formula for our vector field in this particular case. So this is f of x of t. Okay, and the second half of our formula for vector line integrals is you need the velocity vector. Okay, so what you do is you take your path and you just take the derivative of each component. So sine becomes cos. T to the 4/3 becomes 4/3 t to the 1/3, and this one here just becomes -1 minus sine t. Okay, and then we're going to dot those two together. Then we're just going to have a function of one variable. Okay, be careful, your double negative goes away when you multiply these third entries together. Okay, and you end up with the integral of 9.8 times 1 plus sine t, and you just integrate that, right? Plug in your endpoints, and you're just going to get the answer that you get. Okay, you get 9.8 times pi plus 2. Okay, so great. What does that tell us? Like, what are the units here? How do we think about this? Like 9.8 times pi plus 2, what? Like, what does that mean? Okay, and here's how you should think about that. Okay, like what happened as the ball followed this path and gradually went down a curvy hill? Its height decreased by pi plus 2 meters. Okay, and it was having a force applied to it of negative 9.8 newtons. So at the end of the day, at the end of that, vertical offset of pi plus 2 meters, how much extra energy does it have put into it? Well, it has 9.8 times pi plus 2 extra joules of energy put into it, that much extra kinetic energy. Okay, and I mean, like, if you're not a physicist or anything like that, like if you're treating this as like a math course, like all you really need to know here is that the units of the vector field in this particular example were newtons, that's a unit of force, and energy, joules, that's just, force times distance, or more specifically for these units, newtons times meters. Okay, if you multiply those together, you get units of energy, you get joules. Okay, so it's just, what's the difference in its elevation in this example? Well, pi plus 2 meters. So it sort of translated pi plus 2 meters worth of potential energy into kinetic energy via gravity. That's what happened here. Okay, let's do a slightly wonkier example where it's not gravity acting on a ball rolling down a hill. Now it's sort of a wind field acting on a bead being pushed along a string. So suppose that you've got a bead that's being pushed along a piece of string, and the string is arranged in this shape. Okay, if you let t range from -1 to 1 in this path here, that's going to trace out a piece of string in R2. Okay, and the wind is applying a force that's given by this field here, where again, the units are just newtons. Okay, so 2x 1, okay? Then the question is just, okay, find the work done by the wind on the bead. In other words, find out how much energy was put into that bead as it moved along that piece of string. Okay, And so again, the setup here is just, okay, well, work done is a vector line integral. Okay, so here's my vector field, here's my curve, and I just plug things, into the formula for a vector line integral. So f of x of t dot producted with the velocity vector. I've just got to compute these two things. Okay, so on the left here, f of x of t, I'm just taking my vector field here, 2x1. I'm plugging in t cubed plus 1, that's my x, and t to the 5/3 plus t, that's my y. Well, there are no y's down here, so it's just 2 times t cubed plus 1. Okay, that's what goes in the 2x spot. And the second entry is still just 1 because there's no x or y's to plug in there. Okay, and then the velocity vector, what is this x prime of t? Well, just take the derivative of the two entries up here. So you end up getting 3t squared and then 5/3 t to the 2/3 plus 1. Okay, and then same deal as before, just dot product those two vectors together, right? Multiply the first entries together, multiply the second entries together, add them up, and then integrate, and you get your answer. Okay, and so it's a little bit ugly, right? But I'm just taking this, multiplying it by 3t squared, that gives me the first two terms here, and then 1 times that gives me the second two terms there. And then I just integrate all that stuff, plug in your endpoints, and you're just going to get 8 as your answer. Okay, so in other words, this wind, it put 8 joules of energy into that bead as the bead traveled along that path. That's how you should sort of think of that. Okay. All right, we're going to finish up our discussion of vector line integrals by talking about one other notation for them that's in common usage, okay? So like the notation that we've been using so far, remember, is just this notation up here, okay? This means you're integrating this vector field along this curve. Okay, we're going to flip this around a little bit now to sort of write down a more component-wise notation of it, okay? And we're going to try to justify where this notation comes from before I show you what it is, okay? So suppose you've got some vector field, and I want to compute a vector line integral over this vector field. Okay, well, because it's a function from Rn to Rn, I can write it down in terms of its n entries, okay? I've got n input entries, x1 up to xn. I've got n output entries as well, f1 up to fn. Okay, and if I do that, then what I can do is I can take our usual notation for vector line integral and, well, okay, here's my formula for it, and I can expand it out, right? This dot product here, I can expand out and write very explicitly, like, what do I mean by that? Well, I mean, the first entry of this f of x of t, that's f1 of this junk, times the first entry here, that's x1 prime, right? Just the first entry of x prime. Okay, and then plus the second entry of this junk here. So just f2 of all the x's times the second entry here, x2 prime, and all the way down to the end, fn of all the x's times xn prime. Okay, so that's all the dot product means. It just means multiply them entry-wise and then add up, right? Okay, so this integral down here, this is just sort of expanded out notation for the same integral that we had up here. Okay, and now what I'm going to do is I'm just going to switch notation a little bit, change from this sort of Newton notation for the derivative here where I use primes. I'm going to change to Leibniz notation where I use like d variable by dt, like d output by d input. Okay, so I'm going to use Leibniz notation for all of these derivatives, and that's going to sort of let me change the variable in the integral here. Okay, so just copying down what I had before, except now on the right-hand side, I used to have like x1 prime here, and I used to have xn prime here, but that's just the same as saying derivative with respect to t of all of those. Okay, and then what I'm going to do is I'm going to sort of like cancel out the dt's where possible, okay? And this is the step where I go from, okay, yes, this line up here is literally true, down to this line down here, this is just new notation that I'm making up. And the reason I'm making it up is I can just sort of imagine, okay, I'm going to cancel out the dt out on the outside with all these dt's on the bottom. And if I were to do that, then all that's left attached to this f1 is, well, dx1. All that's left attached to this fn is the dxn, okay? And so this, like, it's just notation, but it's notation that you'll see very commonly for vector line integrals. And this is sort of where it comes from. It's not a proof or anything. Again, it's just notation. Like, there's nothing to prove, but this is sort of the line of thinking that leads to it being at least a roughly reasonable thing to do. Okay, and yeah, so this notation, it's called the differential form notation for a vector line integral. And let's just practice doing an example, where we're given a vector line integral in this form, just to make sure that we understand how to use it in case we see it again in the future, which we probably will. Okay, so anyway, let's compute this integral here. And so first off, like we've seen a whole heck of a lot of different types of integrals already. Okay, so make sure that you know how to figure out what type of integral it is. And I mean, the trick here is if you see d's with respect to multiple different variables, that's a vector line integral, okay? Like you can't really make sense of this as anything else. Like when we looked at scalar line integrals, there was only one infinitesimal. There's only like integral with respect to one variable. Here, whenever you've got multiple variables that you're integrating with respect to in the same integral sign, it's a vector line integral, okay? That's the differential form of a vector line integral. Okay, so how do I compute this? Well, like all this notation means, like this is the exact same as just the original version of a vector line integral that we'd seen. All I'm doing here is I'm giving you a way, like I'm sort of writing out very explicitly component-wise, like what is the vector field? Where, well, here's its first component, here's its second component, here's its third component. So I could have written this equivalently as just saying, okay, compute the vector line integral here, where here is your vector field. Okay, those are the same thing. It's just different notation for the same thing. Okay, so how do we do this? Well, okay, like we've got our path. We're going to need the velocity vector, right? So just take the derivative of each of the entries. And like oftentimes what people do is they say, okay, like this here, this means that dx by dt, for example, is 1, okay? Or dx equals dt. And dy by dt is 2t. Just move the dt over to the other side. Oh, dy is 2t dt. And this third entry, right? The derivative of z, dz by dt is 3t squared. Move the t over to the other side. dz is 3t squared dt. And then what you can do when you write it in this way is you can literally just take these and plop them in up here in the relevant spots, right? Oh, dy, what is that? Oh, it's 2t dt. Oh, that can go up here where I see dy. Okay, and what's dz? That's 3t squared dt. I can just plop that in up there. Okay, and when I do this, I get, okay, this was the vector line integral that I was asked to compute, but just make all the appropriate substitutions so that it's only in terms of one variable. In particular, it's only in terms of t, because then you're going to be able to do the integral, right? So for example, in the first term here, what's y? It's just the y, up here, it's the y entry of my path. It's a t squared. And then what's z? Well, it's the z entry of my path. It's t cubed. And what's dx? Well, I wrote it up here. It's just dt. You get everything in terms of t. And when you do that, it ends up looking like this. Okay, now you have a dt attached to all three of these terms here. So we can just pull it all the way out to the right here. Okay, I mean, this is exactly equivalent to doing the dot product stuff that we talked about earlier, right? I mean, like if you converted this back into our usual vector line integral notation, like all that's happening here is these three terms, the y plus z, the x plus z, and the x plus y, like those are the three entries in the vector field. So like you would do f of x of t there. Okay, and then you would dot it with this velocity vector, and that gives you the extra 1 here, the 2t there, and the 3t squared there. It's the same thing we've been doing, just in slightly different notation. But anyway, at this point, it's an integral of one variable. I'm just going to clean up the stuff on the inside, right? Expand all this out, collect like terms. You end up with 5t to the power 4 plus 4t cubed plus 3t squared. You integrate that, you plug in your endpoints, and you just get a final answer of 3. So that's the value of that vector line integral. Okay, and now you know how to do vector line integration, okay? So thanks for watching, everyone. We'll carry on and we'll start doing wacky stuff with vector line integrals starting in the next lecture. We're going to start looking at something called Green's theorem, which connects them to other types of integrals that you'd seen earlier. It's going to connect it to double integrals from multivariable calculus. So I'll see you next time for that. Thanks for watching, everyone.